Section 2.2, the inverse of a matrix. An n by n matrix A invertible. So if we have a matrix of order n by n, which means a square matrix A, and then if we have another square matrix B, such that when we multiply the two, one thing, the product of these matrices from both sides should exist, and they must be equal to each other. And the result should be the identity matrix. Then we say that B is the inverse of A. And actually, at the same time, A will be the inverse of B. Now, the notation for the inverse is this, where we don't read it as A to the negative 1, we read it as A inverse. Okay, this is the notation, and this is something you should be familiar with when you talk about the inverse of a function. We often write F inverse X. So note that in these cases, this is not equal to 1 over f of x. Remember that. In numbers, when you have the negative power, you can write it as 1 over the number. So for example, if you have a 2, what is the number with which you multiply? So to get a 1, because 1 is the identity of numbers, multiplicative identity. So 2 times 1/2 is equal to 1. So it means the multiplicative, well, we have another kind of inverse as well, which is called additive inverse, but we are talking about multiplicative inverse here. So the multiplicative inverse of 2 is 1 over 2. But 1 over 2 is actually, can we write it 2 to the negative 1. So this idea of putting a negative 1 on the quantity and calling it the inverse of the quantity, this is coming from this numbers, because we can write 1 over 2 as 2 to the negative 1. And what is 1 over 2? 1 over 2 is the multiplicative inverse of 2. Why? Because when we multiply these two, we get 1. So when you multiply two things and they give you the identity of the set, then that they are inverses of each other. Anyhow, so inverse. So in the same way, now if you have a matrix B, the inverse will be denoted by this symbol, and you just put that negative 1 on top of the given matrix, and that denotes the inverse of that matrix. Now, does the inverse exist? Well, that depends on the matrix. So a matrix that does not have an inverse is called non-invertible or singular. So theorem 4, it's actually giving us a way or a method to calculate the inverse of a 2 by 2 matrix. So what we do, if we have a general matrix A, B, C, D, any numbers here, then the first thing we do is calculate this quantity AD minus BC, and then we want to have it not equal to 0 in order to find the inverse of A. Now, if this quantity is equal to 0, then we say that the matrix is singular or non-invertible, and we cannot find the inverse. This AD minus BC actually is a determinant of the matrix. It is called the determinant of the matrix, 2 by 2 matrix. Once we have this determinant calculated and we find it is not equal to 0, then we can write the inverse as given here. So A inverse will be 1 over the quantity AD minus BC, which is the determinant of A. So it can also be, sometimes it is given as A inverse will be equal to, and this is the 1 over determinant of A times this matrix. What matrix? This is the same, like we get it from the A matrix. So by doing what? By swapping the A and the D. So the D goes in the place of A goes in the place of D, and the B and C stay there, but their sign changes. So if it was positive, it becomes negative. If it was negative, it becomes positive. So that is how we calculate the matrix, the inverse of a 2 by 2 matrix. So here is an example. I solved the example just for saving time here. So we've calculated AD minus BC, and it came out to be -1. So now A inverse will be equal to 1 over -1 times swapping the A and the D position and changing the sign of the B and the C position. Now remember, 1 over -1 is equal to -1. So I can write it as -1 times this matrix, and then we can multiply the -1, the matrix with -1. So every quantity, each quantity will be, entry will be multiplied, and so we end up getting 3, 5, -1. So that we can say now that A inverse is equal to this matrix. That's how you do the 2 by 2. So what about higher order? What about 3 by 3, 4 by 4, and so on? We have a couple of ways of doing it. One method I will show here, and then another one in the next section. So what we do here, this method, we use row reduction. So we start by writing our matrix whose inverse we are trying to find, and then we augment the identity matrix with it. So this is the step 1. Like this is I would say start. So we start like this. Start. Okay. So we are starting here, and so we have the matrix, our matrix A. And then our matrix, identity matrix. So now you can, so this is A and this is I. Now I will perform row operations on A so that it eventually becomes the identity matrix. So that's what I have done, from left to right, then come to below, and then so on. So once you get an identity matrix in place of A, then the matrix on the other side of the line, of this line, is your A inverse. So now I pull out, let's say A inverse is equal to, now I rewrote the matrix over here, and that's, you can leave it like this, or sometimes it is actually easier because if you have to do some more things with it, or sometimes you have to multiply it with another matrix or another vector, we will see later on. So then you can pull out the maximum, the common LCD of all these values, which in this case is 8. So I pulled out the 8, and I was able to rewrite the matrix with all numbers in there, integers I should say integers in here. So now it's easier to multiply with some other matrix, because with fractions every time you will have to add or subtract fractions, which takes a little bit more time. So this is how you find the matrix.